ETFE-MFM project. My name is Simon Hunkin. I work for Greenovate Europe. Greenovate Europe is a Europe-wide network of experts in sustainable innovation, and our membership is made up of research centres, consultants, and public agencies, all working to develop new sustainable solutions and support their introduction into markets and society. Along with partners in the ETFE-MFM project, we have been producing educational materials for architects and other stakeholders, hoping to broaden and widen awareness of the opportunities provided by textile construction materials and ETFE, that is ethylene and tetrafluoroethylene in particular. Today's presentation aims to provide an introduction to textile-based architecture. It will examine case studies and provide an overview of the current uses of textile-based architecture. First of all, providing an introduction, presenting the development of textile architecture over the past 40 years, before then looking at ETFE in particular, which has been described as an architectural wonder material. Following this, we'll look at the sustainable approaches that can be reached using architectural textiles, and then we'll look at the state of the art, looking at a couple of case studies and looking at the work of the ETFE-MFM project. Unfortunately, our commission speaker had to pull out of the event today. For those of you who are following this lecture, which I'm certain, you will know that at the moment the commission is pursuing its update or recast, as it's called, of the Energy Performance of Buildings Directive. This is currently passing through the European institutions, and the Estonian presidency is hoping to have this directive finalised by the end of the year. What this of course means is for the Commission, they're busy negotiating between the institutions to get this finalised by the end of December. But to give a little bit of background, the European Union is committed to a sustainable, competitive, secure and decarbonised energy system, which it is promoting through the Energy Union and also through the 2030 Energy and Climate Policy Framework. This framework commits the EU to reduce its greenhouse gas emissions by 40% compared to 1990 levels and increase the percentage of renewable energy usage by 27%. Buildings are by far the largest consumers of energy in the world, being responsible for 1/3 of total energy use and around 30% of carbon emissions. These figures exclude the energy and the carbon emissions from the production of building materials. Therefore, improving the energy performance of buildings has become a key priority for the EU in pursuit of its long-term climate and energy goals. The 2010 Energy Performance of Buildings Directive required that EU member states aim to have all new buildings being nearly zero energy from 2020 onwards. The recast, the update, which will cover until 2030, will put greater focus than ever on energy efficiency and energy resources. All of this, of course, means that the construction industry is going to have to adapt, adopting new construction processes and materials that can reduce environmental impact. With this in mind, the European Union has funded research projects working to create new sustainable construction materials, improve energy management in buildings, and promote the use of renewable energy resources. For the past 4 years, our project, ETFE-MFM, has been developing, manufacturing, and testing a smart solution for building facades. It offers multiple functions, including energy generation and facade lighting. As part of this project, we recognise that a major barrier to the uptake of new materials is a lack of awareness and a lack of training on the use of these materials. To answer this, we looked to create new teaching materials that could provide an introduction to sustainable textile-based architecture. These training materials are not focused only on our project, however. Instead, we wanted to design something that could be of interest to a wider audience for those in the architecture and construction sectors. The training materials are comprised of a set of slides and speaking notes, which we will be distributing to universities that are teaching architecture. And those slides form the basis of today's event, which is also being webcast to participants across Europe. And the video from today's event will be made available to universities and to all interested stakeholders after the event. Finally, we're also producing a publication which is targeted more towards architects themselves, presenting some background about the materials as well as case studies on architecture, on textile-based architecture. So before we move on to the first part of the as we are webcasting and recording today's session, we will not be inviting questions throughout the course of the presentation. Instead, at the end of the session, we will have a question and answer session. So for those who are watching online, you may wish to contribute a question. This can be done through the Slido website. So this can be found at slido.com, and the code for this is H708. Then at the end of the presentations, I'll be able to see all of the questions which have been submitted, and we can put those to the panel. For those who are following the web streaming, please identify yourselves in your written questions. If we know roughly the background of who is submitting the questions, then it can help us to give a clearer response. For those of you who are here today, of course, you can simply note down any questions that you have during the event and ask them at the end. Or you can also contribute via this Slido platform. For those of you who are into Twitter, you can use our ever so catchy hashtag ETFE-MFM, and we'll be able to track your thoughts through the event. And my colleague Valeria will be live tweeting throughout the event, so you can see and share what she's writing on our Twitter account, which can be found at Greenovate EU. So the first part of this presentation is a general introduction to textile-based architecture, which will present the development of textile architecture over the past 30 to 40 years. To give this part of the presentation, we have Juan Ramón de las Cuevas, who is project manager at Acciona Infraestructuras, one of the world's leading companies in sustainable construction. Acciona works across the entire value chain, including development, engineering, and construction, looking to find new ways to integrate innovative technologies. Juan Ramón holds a master's degree in mechanical engineering from the University of Seville in Spain, and has more than 10 years of experience in energy efficiency and green energy supply for buildings, district, and cities. So with that, Juan.
Thank you, Simon. Thank you. I don't know if you hear me well. Hello, everybody. Thank you, Simon. Thanks for the introduction. Thanks for coming here today. Well, as Simon was pointing out before, I'm going to be the first one to speak today. I'm going to give you a brief introduction to what we have been doing, tracing the origins until nowadays. The presentation will have 3 more parts. My colleagues will be in charge of them. But my role today would be, let's say, to introduce you to what is this topic of textile architecture. In principle, we're going to be moving through history. Let's say we're going to take a look at where are we coming and how was this originated. And the best way for us, let's say, to explain how have we come up to this project is to be showing a sequence of the evolution for everybody to, let's say, take a look at the possibilities of these materials today. In principle, the origin of what we can call textile architecture is pretty old. We can see the picture over there of a tent some 1,000 years ago. This was a dismountable structure. It was made to give environment and rain protection. It was made of the fibers they had at the moment, and there is another example here in this slide where you can see let's say wind and sun protection element made of probably cotton fabric, which was called the velarium in Rome in the Colosseum. These elements were what can be considered today as the origin of textile architecture. In the Industrial Revolution, the petrochemical industry was strongly developing, and the plastic industry was providing new materials and new applications of plastics. This was the origin of a new wave of possibilities for this kind of materials in many industries, but also in the construction sector. By this, these new materials were, let's say, possible to integrate in different varieties. Here you see a different, possibilities, because according to the organic chemicals, the possibilities are almost infinite. The combinations are really high, and there are lots of different solutions with different properties, with different applications and with different possibilities, depending on the utilization you want to make of them, depending on the type of building and the type of element you want to make with it. Transparency, light transmittance, fire resistance, load bearing capacity. There are lots of properties and there are lots of materials with a wide range of parameters for each of those characteristics. In principle, these materials can be used for lots of, let's say, building components. I mean, the possibilities are immense. You see there are some pictures of examples. Most of them are elements related to the building envelope, as you will see. Typically, their utilization is related to aesthetic use of these materials, and as you can see in the pictures, the spaces covered by this material can be open or can be indoors of the buildings, and most of the utilizations are covering different building typologies, typically with the exception of the residential use, which is not in any of the pictures you can see over there. So commercial buildings, leisure, industry, lots of sports buildings have these materials on them. We have been building some stadiums with this material in Spain and other places. Now we are participating in the construction of the new airport of the city of Mexico, and in the original plan there is the intention of including ETFE applications. We will see if this is possible and to what extent, but the plans are over there. Going back to the origin and showing now you a number of examples, you see there in the picture 1957, this is made of cotton. This is one of the first applications in Germany. Combination with PVC. It's an open air canopy, and this is one of the examples that is, let's say, combining the origins of this textile architecture with the plastics. There in the picture in this new slide, you see the customer center roof, let's say, prepared for clients to stop their cars and to wait for the mechanics and the people from Volkswagen to come and help them with the protection of the rain, but in an outdoor space. Obviously, this is more an aesthetic monument, an element, rather than an energetic one. The ETFE can also be used not only as a single layer or multi-layer element, but it can also be inflated. Let's say there's a pneumatic press stress. It's like a cushion. It's something like a pillow, and this is done with the principal benefit of the thermal and sound insulation. There are lots of examples, and this is one of them in the picture from 1970. It's in Japan. It's a singular monument, it's a singular building. It's for a Universal Expo, so it's probably with plenty of budget in it for those days. And in relation to the lots of, let's say, possibilities and lots of ways of implementing these materials, the prefabrication and the manufacturing and the installation techniques are also really different depending on the application. There on the right side of the screen, you see a really singular building, which is the headquarters of the Omega company in Switzerland. It's made of modular pieces. So for the manufacturing and the transportation on site, you can see that there are different operations to take care of, and somehow this is, let's say, conditioning the design of the whole building and the design of the operations for the construction process itself. Whereas on the left side you have a picture where there are two big machines preparing a wide piece of textile, which is, let's say, transported, the whole of it, to be installed on site. The installation is much more, not complex, but let's say totally different from the other one. In relation to the applications or to the use of the textile, depending on the type of building, depending on the type of project that you want to make a reality with this material. There you have an example which is quite singular. It's a tower to test elevators from the Thyssen group. It's a curtain wall. It's made of PTFE and glass meshes in Germany. And well, as you can see, the utility of this material is single. So the only utility is to separate the exterior from the interior, to test the elevators according to the regulations and the conditions of this manufacturer. However, the textiles can be having different, let's say, functions in combination with other technologies. This is somehow the origin of our project. We have been making a multifunctional element, and this example here in the picture is showing you one of the applications that we have been integrating in our solution with the illumination system made by LEDs. Okay, this is a picture from 2010, and it's another building in Japan. Here again we have another utilization with a 3-layer cushions. So this is inflated material. This is an example in Germany. It's a waste management authority car park. In principle, according to the utilities, here we are not illuminating, but we are integrating photovoltaic technology on the surface of these pillows. Okay, so they have, let's say, two functions. One is insulation and protection, and the other one is electricity generation for the building. The structures and the materials can be used in all its possible combinations in two ways. I mean, the typical application is to use it for permanent buildings, but however there are also examples use it for temporary, let's say, implementations of this solution. This is another example from a building in the United Kingdom, constructed for the Olympic Games. So its issue for the Olympic time is, let's say, limited, at least that time. And as a permanent structure, there are lots of train stations and singular applications like this in the open air. This is a recent project in Poland, where the application is let's say, for a public building, and the aim is to be there, let's say, for the entire lifespan of the building. Okay. The properties of the materials are still under development, and some of them probably will have to be substituted or replaced. But in principle, this is one of the applications that we consider as most relevant these days. As I was saying before, in the airport of the city of Mexico, the plan, the original design was done by Norman Foster, the British architect. We are planning to integrate permanent ETFE solutions. We would like to see the level at which it is possible to do that, because the project is really, really ambitious. But in principle, this is one of the new utilizations that are, let's say, it's a total actual example. Okay, that is all from my side. It's section 1. I hope it was clear for you. Some questions maybe for later. Thank you.
Thank you very much, Juan Ramón. Our next speaker is Professor Karsten Moritz. Karsten is Director of Research and Development at Taiyo Europe. He is also Honorary Professor for Membrane Structures and Materials at Hunkin University of Applied Sciences in Germany. Taiyo Europe are one of Europe's leaders in textile architecture projects, providing project planning, consultancy, as well as project management. Karsten has degrees in architecture and structural engineering from the Leibniz Institute of Hanover, and he wrote his doctoral thesis on ETFE foils at the Technical University of Munich in Germany. Karsten researches the mechanical behavior of ETFE foils, pneumatic structures and membrane structures in general. And this part of the presentation will present ETFE in detail, looking at its reputation as an architectural material.
Thank you very much, Simon. It's wonderful. Thank you. Yeah, thank you very much for the introduction. Not possible? Okay. I'm sorry? Yeah, I would like to tell you something about the advantages and disadvantages of the material ETFE. ETFE was developed in the year 1970 for polymer, and it's something like PTFE. Maybe PTFE you know, it's a brand name Teflon. Yeah, you know Teflon from many articles in your kitchen at home. It's very slippery and it's a plastic material. And ETFE is similar but a little bit different. It's a thermoplast. Now you can melt it, and afterwards you can recycle it, and you can use it again because it's a property of thermoplasts, plastic materials. And on the right hand side you can see a project we realized, or Covertex realized, in the year 2002. It's a Mazoala rainforest in the zoo of Zurich in Switzerland. 10,000 square meters ETFE foil cladding or envelope. The gable sides here at the end, here, and the other side, as well as the cladding here on these curved sides. Originally it was a 3-layer system or triple-layer system. That means 3 layers of ETFE foils and in between air, nothing than air, with a low overpressure, approximately 300 Pascal. That's really nothing. If you go in a high-rise building from the 1st to the 3rd floor, it's nothing else than 300 Pascal. It's really nothing. It's just a little bit of overpressure to stabilize the films and to get the films or the foils wrinkle-free. There was a story behind this building. Let's say 10 days before commissioning date, when we handed over this project to the client, there was a big hailstorm exactly above this location. And this hailstorm damaged the outer foil of these foil cushions. Many hundreds of holes were in the foils because it's a very thin film, 0.2 or 0.25 millimeters only, 250 micron. You can imagine that a hailstone with a diameter of 75 millimeters, these stones were so big, with sharp edged surfaces. You can imagine that the foils are damaged. Many holes in the outer layer. But the other 2 layers were still intact, were okay. Only the outer layer was damaged. And then the insurance company investigated this hailstorm and the damages, and after 4 weeks they decided, okay, it was not a mistake we have done in our planning and design. It was something like a God's will, and nobody could imagine before that hailstones with a diameter of 75 millimeters occur. So the insurance company paid for this damage, we repaired it, but the insurance company said, you have to add a 4th layer on top for replacement if something like that, something like such a hailstorm occur and again. And indeed, a few years later, another hailstorm damaged this so-called sacrificial layer or additional layer, and we could replace this 4th layer on top very easily. So you can decide by yourself if it's an advantage or a disadvantage of this material. It was damaged, but only the outer layer. But if you build such a cladding or such an envelope made of glass, and the glass breaks because of the energy of these hailstones, everything is damaged. The birds can fly out, and everything is damaged, also the things below. So, in my opinion, it is an advantage of ETFE foil. Even the outer layer was damaged by many hundreds of holes. Only one example. yeah, ETFE or wonder material, I think it is a little bit too much honor for a material, but of course it has some different properties and special properties. If you think here this glass window, the glass pane, I would never use ETFE foil instead of glass here. Everybody compares ETFE foil with glass. I don't want so. Yeah. Here you want and you get and you take glass windows. And here, for such a cladding, such an envelope, ETFE foil is a good material. Why? You can print it with different dots or different patterns. You can, or with the printing you get a shading coefficient. The energy input is much lower, the transmission is lower. And it looks like to be a little bit opaque, but only from outside. If you take a look from inside to the light sky, you can look through, even it is printed. One advantage. Another advantage is the price. ETFE foil cushions cost, let's say, 50% of a glass roof, like that. The price is always a big issue for clients. And if the durability is enough, some clients will decide for ETFE roofings instead of glass roofings, of course. Yeah, durability. The first permanent ETFE roof has been built in the year 1982. It was a mangrove hall in the zoo of Arnhem, Netherlands. 1982, that means ETFE is meanwhile 35 years old. And they replaced the ETFE material, I think, 2 or 3 years ago. That means you can imagine a lifetime and durability of more than 30 years. We know, meanwhile. In the first years, we were not sure what is the durability, how long can we use the material on top of such a roof. But today we can say, okay, 30 years, it's not an issue, not a problem. Maybe I go back again. The reason why the client decided for the cladding to be done or made of ETFE foils was not only the price. One big advantage is the transmittance of ETFE foils in the UV spectrum of the solar irradiation. Plants like these palm trees here or the rainforest needs UV radiation, otherwise they cannot survive. And that's the reason why ETFE is used for botanical gardens, for swimming pools, and also for big stadia. If you have a pitch with grass and you need sunlight and UV radiation for the growth of your pitch or your grass, you need an ETFE foil roof. And that's the reason why more and more stadia are equipped with ETFE foils instead of glass on top. Another advantage is that dirt and water, or let's say the water or the rain, will clean the surface of the ETFE foils. You don't have to maintain it, or you don't have to clean it every year or in an interval, because it's cleaned automatically by the rain. That's also a good advantage of ETFE foils. Another advantage is the weight. ETFE, or the weight of ETFE foil cushions is, let's say, 1 up to 3% of the weight of a comparable glass roof. If you think a glass roof has a weight of, let's say, 30 kilograms per square meter, and one ETFE layer of 350 grams per square meter, it's really a big difference. And therefore, ETFE foil cushions are used the last years also on big cruise ships. We realized a few years ago to ETFE foil domes on the AIDA Prima cruise ship, and the second one will be finished this year, also with ETFE roofs, 1,000 square meters each foil dome. And the reason is these ETFE foil domes are on top of the roof of the cruise ship. That means on deck 17. And if you think about the center of gravity of a ship, the weight of such a big roof on top of the ship is very important for the structure of a ship and to reduce the weight on top of the ship. Another advantage is like an arched truss, like this one here, like a cable, supported cable, whatever, to support such ETFE foil cushions. 4 meters is a lot. It's more than if you would take glass panes as overhead glazing. That's maybe also an advantage. Here you can see the advantage of the UV transmission. This is a solar spectrum of the sun, and here on the left-hand side, you see the UV spectrum, and it's a comparison between ETFE, it's a red line, glass 6 millimeters thick, and polycarbonate. And this is a polycarbonate line here, or graph. This is the glass, and this is ETFE. That means the transmission is nearly 80%, that is 100, 0, and glass and polycarbonate have a transmission which is nothing. So that's the reason why ETFE is used for plants and stadia and so on. Yeah, I already mentioned you can print ETFE foils like that here, different print patterns with a different number, printed on transparent film, printed on a blue film. This is a UV cut film, other printings, a blue film, transparent film, matted films, and white films. All ETFE foils with different printings, different colors, whatever, have different optical values and optical properties. It's evident, I think. This is a chart that is showing the durability. It is a chart of the tensile strength here, which is reduced after 15 years, let's say 15% lower. After 15 years, the tensile strength of the material compared to polycarbonate and glass here. And this is a development of the transmission, light transmission. After 15 years here, you will lose, let's say, 10% of transmission. So the material is changing a bit, of course. You will get no material without any changing, but the degradation or abrasion and the reduction in tensile strength and transmission is really low. You can build with ETFE as a single layer construction. Here, ETFE foil, supported by cables, double layer cushion or a triple layer cushion, for example. Here is the span width, let's say 4 meters. Here, the span width between the cables is much lower. Single layer constructions are or the span width of single layer constructions are lower. That means 1.5 meters in maximum, depending on the outer loads induced by wind or snow. U value, because related to the thermal insulation, ETFE foil cushions are not as good as glass structures. Today we achieve a new value of 3.0 watt per square meter in Kelvin for a double layered ETFE foil cushion, and 2.0 for a triple layer system. Meanwhile, we also built cushions with 5 and 4 layers, and we achieve U values of 1.5, let's say 1.3 in maximum. And if you compare it to glass, you get windows meanwhile with a value of everything. So it means UV, U window of 1.2, 1.0, and sometimes better. So this is a disadvantage at the moment, but we are giving our best to improve also the thermal properties of such structures to get structures Kate maybe also with ETFE for us. Thank you very much.
Thank you very much, Karsten. Next speaker will be Dr. Rosa Lagunas, who is Director of the Photovoltaic Solar Energy Department at CENER, the National Renewable Energy Center of Spain. Rosa was responsible for the definition and startup of this department back in 2002, which works on research and development projects, testing activities, and technical consultancy on photovoltaics with partners and customers from around the world. As well as her role at CENER, she also participates amongst other activities in committees for the development of PV standards within the international community, in the scientific committee of the European Photovoltaic Solar Energy Conference, and she is also a member of the executive committee of the International Energy Agency's Photovoltaic Power Systems Program. Thank you, Rosa.
Thank you very much for the kind introduction. Well, I'm going to speak about textiles for sustainable buildings, thinking on the fact of sustainability added to the buildings when you have the possibility of including the energy generation in the same building itself. So textile that is going to have some functionalities related to the inclusion of the capacity of generating electricity, in this case through PV technology. Again, we already saw the possibilities of the ETFE material, sustainable. We saw their inclusion in different interesting buildings, specific buildings that could not have another kind of material for that, like the greenhouses and those kind of things. And now I'm going to speak about the ETFE as let's say passive material, staying there, just being part of the building, and active material when generating electricity itself. As Dr. Moritz said, ETFE is recyclable, easily repaired, it has a lot of advantages, and it's quite versatile. But let's say, in the case of the greenhouse, we see here on the left that is just using their properties for housing. In the case of the right picture, here the architecture itself, the material itself becomes active, generating electricity, because what can be seen here are the PV cells that are integrated in the same material. Then we have the generation of electricity close to the building. An example of passive design is this stadium where, let's say, the roof includes several layers of foil, so we have it there. There's also a portion of canopy transparent to ensure maximum levels of sunlight, and there's also another section that also covers some of the seats. This is in Bilbao, and in Bilbao rains a lot. So again, there are many opportunities for this material to be used on different applications in the buildings. Then, active design, what I was saying before. Active design means that you can obtain something out of the material. So this is an example of the ETFE material that has integrated some photovoltaics on it. There is specific technology, let's say. Something that I will say later is that photovoltaics is not just one technology, there are many different technologies, and then you should use the best technology for every application. So this is an example of technology, and remember we are at the beginning of doing this type of integration of photovoltaics into this material. Maybe there might be more elegant options, maybe for it. However, let's say, if we think in photovoltaics, maybe most of you know this type of PV modules. And then if you put those PV modules on the roof of a house, you have also a generation there. But this is named building added photovoltaics. You just put a PV module on the roof of a house. In this case, it has more, let's say, it's more useful because in this case, the PV is also giving some shadowing to the building. Instead of putting just a standard shadow, you put the PV modules as acting as a shadow. So this is building integrated in the sense that, okay, we are substituting some material for something that already generates electricity. Then in this case, maybe I should use that. This is an example of building integration. This is another technology, not the one crystalline silicon you saw before. This is another technology, and it's like a part of a facade. And then, in this case, what happens is that we have substituted the material of the facade for this one that has the possibility of generating electricity. Then we are saving the cost. The final cost is lower than if you had the facade and added something on it. So this is the advantage, to have a constructive element that has the possibility of generating electricity, as it happens in this case. So it's multifunctional, it's a facade, and at the same time it produces electricity. This is an improvement with respect to building added, where you just add something, so you add cost to the building itself. But again, speaking about the different technologies, you saw the first picture with the crystalline silicon technology, very good technology. It's almost 90% of the production of installation worldwide of the PV technology is that. Very good efficiency. Now we are almost 20% in a normal way on the installed technology. And nowadays, of course, the record is 26-point-something% efficiency, which is very good and increasing. It has a limit, but it has many possibilities. But again, it has some other drawbacks. For example, it's something that is, let's say, rigid, or at least if you want to give a curve on something, it's just a question of doing, let's say, slowly in order to be able to curve that technology. However, you saw these things that we had integrated. The advantage of some other technologies, the main thin film technologies, is that they are not so thick as the crystalline silicon. They can be deposited onto different substrates, therefore they can be deposited onto flexible substrates or curved substrates, and then they have some other applications. So this is the message. Of course, it's very interesting, crystalline silicon technology and some other crystalline technologies that have a thick substrate, but there are some other technologies, thin film technologies, that are going to be deposited onto any material. So they are going to be more capable of giving some other, let's say, maybe more flexible appearance in the aesthetics part of it. Then these technologies are based on different kind of materials. Let's say we have technologies like silicon-based thin film, gadolinium gallium selenide, cadmium telluride, and OPV technologies. OPV technologies are the newcomers here. Those ones, the first ones are inorganic components. The OPV has organic components. The difference is interesting. Usually the organics are much cheaper than the inorganic ones. Of course, they have also some other problems. Let's say they have some other risks to reduce their efficiency. At the beginning, they are not as, let's say, efficient as might be some of the standard technologies. However, they are newcomers. They are under development at this moment. But all of them have the advantage of being able to be deposited onto flexible substrate. This example here is an example of an OPV technology that is flexible and can follow the curve of the cushion that was on the ETFE. Speaking about organic-based PV technology, which is quite new, I mentioned a word that maybe you will recognize in the near future. This is the perovskites, the newcomers. in the 3 years of development, this technology has gone up to 20% efficiency. It's cheap, it's a good advantage, and it's also, let's say, we can consider the hybrid inorganic technology. At this moment, it has some other weaknesses, and the weaknesses are related to what I mentioned before, the degradation, which is not still very well controlled. However, there's a lot of activity worldwide concerning this issue of having capacity enough to encapsulate these materials to allow not losing efficiency in a fast way. So again, keep perovskites in mind, because they will be the newcomers for this one. And for example, in this case, this is one BIPV, because it's the building. This is a PV technology to the PV, because it's a PV by the company Obvious, which is pure organic, and it was integrated in the German pavilion on the Milano fair. The German pavilion built also by Taiyo. However, this is an association between the company making the PV and the company making the building itself. But let's say there's some things. If you're going to have something in the building, you should be very interested in having a product and being close to the people. It must be safe. It's a key aspect, and also be durable. So the element that is going to generate electricity also should be supported by the regulatory aspects of every country concerning the use of electricity in the buildings and close to the people. So in all those aspects, when defining or designing a BIPV product should be considered since the beginning. Concerning specifically the photovoltaic part, there are some standards that should be really that should be used to evaluate the product. There's one standard related to safety on electrical, on let's say mechanical, on all aspects concerning the PV technology. There are some other standards related to design qualification and type approval. We have to do with durability, and all those aspects are required by the market in order to accept the product to that. And again, when you are going to make a building, you must have everything combined. You must have your product, your constructive elements should pass tests related to the PV part and also to the constructive part. So again, a product that's going to be installed, is going to be used in close in the buildings, close to the people, should have been tested in a very, let's say, serious way on many aspects itself. Testing aspects like durability, testing aspects. The message is, I said maybe too fast, but there are many different technologies. We are at the beginning of this BIPV world, and the future is for sure close to it. However, we should be very conscious on the possibilities of the technology, on the fact also that the integration of the PV, of the photovoltaic technology, has some costs. The costs are that, for example, for a big PV plant, you choose the optimum orientation, you choose no shadowing, etc. But for a building with BIPV, you're going to have a building in the middle of a city, maybe not perfectly south-oriented, maybe vertical, which is not oriented to the sun. So all those aspects will make that the generation is not going to be as good as it should, as it is on the standard big PV plants, where they are optimized concerning the conditions of solar resource absorption. Then, accepting that, keep in mind that we are going to have two uses, the building and also the PV. So the mixture of everything is going to be an advantage, and of course the generation close to the place of use is the biggest advantage of this technology. So lower losses, independence of the place where the energy is generated, etc. Again, essentially, for the development of BIPV is a question of synergies between PV and construction elements, and this is what we all hope to become in the near future a commodity.
the next section will present a couple of case studies, state-of-the-art uses of ETFE, and for this we'll invite back Dr. Karsten Moritz to present these two case studies.
So I sit down better, I learned. Yeah, I would like to show you a few examples with ETFE files. You have seen already a few slides about the AWM project in Munich, the combination of PV modules and ETFE for cushions. Yeah, the technology is a 3-layer system. It means outer layer ETFE, inner layer ETFE. The inner layer is printed to achieve a shading for the trucks that are parked below this transparent roof. And in between there's a middle layer and mechanically fixed PV elements on this middle layer. And you need an air circulation in those cushions to reduce the temperature for the PV. And you know the PV is also generating temperature by itself. And we wanted to avoid that the temperature in the cushions is too high. So it should be normally less than 60 degrees. Otherwise, the mechanical behavior of the ETFE foil will change and will decrease. So the tensile strength and also the yield stress. And the material is getting weaker and weaker with the temperature, and that is also to avoid. And therefore, you also need an air circulation in such cushions to transport or to transfer the temperature or the hot air to the outside. Yeah, the roof has a size of 8,000 square meters approximately and consists of 220 of such air-supported cushions. The air was supplied by an air blower unit. The energy consumption of such an air blower unit is normally approximately 3 kilowatt. It's not so much. If you also if it's running the whole time, 3 kilowatt is not very much. One issue is that the geometry of the roof was fixed before because the old roof was collapsed a few years ago, and the authority or the government of Munich wanted to get a new roof, also a membrane roof, but in this case with energy generation by the combination of ETFE foils and PV. The former roof was a fabric membrane roof. The reason why it collapsed was I think the maintenance was not as good as it should be, and therefore the drainage system was frozen, and that led finally to an increase of the snow load and the water pond load, and therefore the very light and slim roof collapsed. Fortunately, nobody came to death, and the damage was low, but it was really a disaster. And this is the new roof here with a PV. This is a top view of the roof. It is completely irregular. It is something like a modular structure. The roof, or the PV of the roof, should deliver 124 megawatt hours per year. And we are measuring every year the output and the energy generation. Of course, it is getting lower and lower, and normally you guarantee a power output of, let's say, 90% of the original one after 10 years. A second example is the Allianz Arena in Munich. You know this building maybe. It consists of 2,800 ETFE foil cushions. And the reason why they decided for such a envelope made of ETFE was in the first line the architectural appearance. And you can see by yourself that also the illumination is brilliant of the stadium. Initially, the client decided for neon tube lamps, white light with filters before in front, filters blue, white, no white not, blue and red. And I said the third filter was green. Meanwhile, the neon tube lamps are replaced by LED. So today you can get every color you want, or many, very big number of colors, and the energy consumption is much better because of the use of LED instead of neon tubes. This is a photograph from the installation process. Each romp has a size of 16.5 meters in maximum in one direction of the romp, and in the other direction, let's say 4.5 meters in maximum. The workers are working on cable nets or on working nets that are spanned or fixed on the steel trusses below. The big difference between glass paints and ETFE for cushions is the horizontal force. You can imagine if you pump it up and supply this ETFE for cushion here with an inner overpressure, you get tension here in the outer layer and in the inner layer, and this will lead to horizontal forces here at the boundary. And that's completely different to a glass structure. You cannot replace a glass pane by an ETFE for cushion. It's impossible, because you have to improve and to restrain or strength to your primary structure here. But on the other hand, if you think here is a span width of 4, sometimes up to 5 meters, related to the outer loads of wind and snow, the span width is much bigger than for glass panes. That means the the distance between the primary structural elements are much bigger. And if you think that this is only a film made of 250 micron, and this one as well, and in between there's only air, you cannot build lighter. It's an optimal lightweight structure. Even there are here horizontal forces. But in total, if you add everything, the weight of the cushion and the weight of the primary structure, you can reduce your self-weight a lot. It's the best lightweight structure you can get. And if you think about the multifunctional options you have to integrate PV, to integrate solar collectors, to have pneumatic controlled shading systems inside, it's also a kind of lightweight structure if you build a multifunctional surface structure. So finally, you get all kinds of lightweight structures you can imagine by using ETFE foil cushions. It's a really big advantage. Okay, back. This is a photograph of the horizontal surface on top of the roof of the Allianz Arena in Munich. It's a uniformly distributed snow load, and you can increase the inner pressure in the cushions if the snow load is too big. But for example, in Munich you have a design snow load of let's say 1.0 kilonewton per square meter. That means 100 kilogram per square meter snow load. If you want to get an equilibrium between the inner overpressure in the cushion and the snow load, you need an overpressure of 1000 Pascal. This is the same than 1 kilonewton per square meter snow load. Otherwise, the outer layer will go down and will squeeze out the air from the cushion back through the air inlet. And that happened in history, and therefore the planners decided to get a drainage tube here inside the cushion. This drainage tube is made of aluminium and it is connected to the outer layer, and here it goes through a valve in the inner layer. And if the snow load exceeds the inner pressure, the outer layer will slowly lay down on the inner layer. And if the snow is melted after a while, when it's getting warmer, the water can drain here through this pipe to the ground. That's something like an emergency drainage system. We had no other chance. What can you do? If the snow load is too big, it's working like a bathtub. And if it's completely full with melted snow or with water, you have to drain it, otherwise your primary structure will collapse. That was the only option we had. Another option is maybe to use pumps on the roof, but try to pump water, thousands of cubic meters of water from a roof in a height of 50 meters within a short time frame. It's nearly impossible. So we had no other chance than to design such a drainage system. Another example is the National Aquatic Center in Beijing. It's an indoor swimming pool complex, very nice. You can illuminate it with different colors. Yeah, we would like to come to the next and I think last chapter, given by Armando. It deals with new developments. That means with our research project we have done together. That are the project partners, and this research project was funded by the European Commission. Thank you very much.
Thank you very much, Karsten. Now our last speaker, this is Dr. Armando Menéndez Estrada. He is the coordinator of the ETFE-MFM project. He is also a researcher in the field of photonics at ITMA Materials Technology in Spain. ITMA performs research and development activities in materials, products and services that include at how new technologies can be applied to materials in order to contribute to the establishment of new economic and business activity areas. Armando has more than 10 years of experience in the analytical characterization of thin film photovoltaics, with expertise on thin film solar cell development and building integration. Armando is going to present the ETFE-MFM project and the work that we've been doing for the past 4 years.
Thank you very much, Simon. Well, as it was explained before, this is a European project. This is almost at the finish of the project, because at the end of this month this project will be finished. So we are getting the final results of the project now. Well, I'm going to talk about a little bit about the project and the final demonstrators we have already installed on facade, and I will show you here in this presentation in a few slides. As Karsten said, this is the consortium of the project. We are six partners, and the objective, well, the main objective of the project is the development of a new ETFE module with different functionalities integrated on this module, such as photovoltaics and illumination devices based on LED technology. Well, I'm going to try to explain a little bit how are these modules, these multifunctional modules we have developed. Later I will show you a video where you are going to understand perfectly what we are talking about, but let me say something about the modules. For sure, the modules are composed by two ETFE layers, one on the front and another one on the back. And in the middle, there are the different layers, different sheets that compose the multifunctional module. when I talk sheets, different sheets, I'm talking about the photovoltaic organic photovoltaic modules. These modules compose one sheet. Other sheet are the LEDs devices, LED strips along the module, and there are another sheet. Is a polymer EVA. It's a polymer for the lamination. It's encapsulating. Is encapsulating material, so it's used for the lamination of all components into a unique element. The objective is to create a permanent element for building facade. And well, the sector, the application can be different depending on the final application. Here I can show you the first demonstrator we made. This demonstrator was installed at the roof of the National Renewable Energy Center of Spain, CENER. Is installed at the roof, not in facade, but in vertical position, simulating the real position in a facade. And we designed this module as a preliminary test to get the preliminary results in order to know how to develop, how to manufacture the final demonstrators. Here you can see the picture of the module during the day in the night. And as you can see, we use small organic photovoltaic modules on the module. And also the frame is not the final design of the frame, but the results obtained from its installation and its performance gave us many information about how to proceed with the final demonstrators. Well, here you can see the final demonstrators installed on facade, on ITMA building facade. We designed 4 multifunctional modules with a total area of 9 square meters. And we decided to design two different designs. These 2 modules have the LEDs on top of the photovoltaic modules, and the other 2 modules are another design with the LEDs underneath, behind the modules, the photovoltaic modules. Where these demonstrators were installed this summer, at the beginning of this summer, in June, and we are monitoring and evaluating their performance during these months, and we will get the final results right now for the commission. Well, the market potential for these kind of modules, from our point of view, it's clear. Nowadays the architects are demanding this kind of illumination on the facades, mainly in singular buildings. These multifunctional modules provide the answer for this demand, giving the possibility to create very big screens on the facades. The advantage of this project is that this facade, these modules are able to create energy, because the photovoltaic elements on the surface convert the surface in an active skin, and the power consumption of the illumination can be provided. The energy consumption can be provided by these elements, and the potential uses of these modules. Obviously, we are not talking about residential buildings. We are talking singular buildings like stadiums, shopping centers, public buildings, museums, this kind of buildings. And now, to understand perfectly what we have manufactured and installed on the facade, here we have a video. I don't know if yes. Yes. Okay. Perfect. Okay.
Facade lighting is becoming the medium of choice for outdoor visual messages, with rapid growth over the past decades. However, such use can be very energy intensive. What if the required energy could be generated at the point of use? An interdisciplinary group of experts has come together to explore a new way to support the sustainable use of building facade lighting. To provide energy production and lighting, they combined LED strips and photovoltaic foil in one module. This way, energy can be produced and used within the same element. This module is then encased by a material called ETFE. ETFE, or ethylene tetrafluoroethylene, offers up to 95% light transmission. It is elastic while being very structurally resistant and has great longevity, as ETFE does not degrade and is easily repairable and recyclable. A building in Avilés, Spain is being used as a demo site. The headquarters for ITMA Materials Technology now also serves as a demonstrator for ETFE multifunctional modules. Two types of modules have been installed. The first version consists of a layer of ETFE foil at the front and back. Then comes a layer of photovoltaic foil, followed by a layer of light-emitting diodes, short LED strips. This gives prominence to the LEDs over the PV. In between each layer is a special material called EVA, or ethylene vinyl acetate, which keeps all the different parts together. In the other module, ETFE foil and EVA stay the same, but the photovoltaic layer and LEDs are switched around to give the PV prominence. First come the lights, and on top of that lie the solar cells. The layers are installed to maximize the amount of light reaching the photovoltaic foil while ensuring visibility of the LEDs. Two of each module type are installed on the building for testing, to see which has the best performance for both lighting and energy generation. During the day, the PV foil absorbs the sunlight and generates energy. This energy can be sold into the grid or stored in batteries. During the nighttime, the LEDs light up. The modules can be used to transport different types of media, such as a video or marketing messages. ETFE multifunctional modules have a great potential for future commercial architecture. Displaying messages while producing their own energy can change the way we think of facades and make these buildings more energy efficient. Combining aesthetics and efficiency is challenging. The solution lies in specially developed technologies. For example, whilst this organic photovoltaic foil is not as efficient as traditional PV, it has other advantageous qualities, such as higher transparency and flexibility.
We wanted more efficiency, more energy production, to have more hours by night with the LEDs lighting. But from the aesthetic point of view, this technology is really, really good. It's very attractive for the architects. So in the future, maybe with a better devices, the module will be perfect.
To optimize the energy production of the module, the materials need to be perfected for use. LED strips need to work hand in hand with the photovoltaic foil. The team is working together to find faults and fixes to prepare the modules for the competitive market. The energy production and consumption of the modules are carefully measured and analysed to help find the right balance between visual performance and energy generation. The two module configurations perform differently, with one generating more energy, but the other acting better as a screen.
The first thing to do to commercialize these modules is to develop the industrialization of these modules. This is a step before the production of the modules to reach a very low cost of the production. Maybe in 5 years, I hope that this product, this development is start on different facades around the world.
The ETFE multifunctional module can be used for monumental architecture, turning plain facades into screens.
So this is the video we have made to explain a little bit how is the objective of the project and which are the main results obtained from it. And just a summary of all of these talks we have made today here. Well, in principle, it is clear that the textile architecture is highly demanded by the architects due to its special properties, because give the possibility to the architects to create new designs with new functionalities. In this case, in the case of ETFE, Karsten explained it perfectly. The properties of ETFE, of this material, is the most suitable material for this kind of architecture. And in this project we are combining these two things, the textile architecture based on ETFE polymer and the integration of different functionalities to the modules in order to create a new material, is a new building element that can be very interesting for the architects. Obviously, there is still a hard work to do. The research is going on, and obviously further developments of this kind of materials are expected, and we will have new ideas, new designs in the next few years. So thank you very much.
Thank you very much, Armando. I request all of our speakers to come to the front to be held. Share the microphone now. Okay. So we have a couple of questions in through the online system, but we can go first to the room. Anybody have any questions for our panel today? Yes, please, before asking your question, just present yourself a little bit about what your organization is.
Okay, hello, my name is Ronald Jansen. I'm the coordinator of the Reinterest project in Belgium, financed by the Walloon region. We try to make multifunctional quadro technologies, facade elements containing insulation, batteries, PV, and monitoring and conversation with distribution service operators to allow demand-side management and regulation of heat pumps. My question is to mimic existing facades in urban areas. We think ETFE could be very interesting if it's 3D printable. Is ETFE 3D printable?
You said 3D printable, right?
Yes.
That means any surface structure printed. So
yeah, because existing facades are not flat.
Yeah.
So if we are willing to comply with urbanistic regulations across various cities, we have to somehow tell the urbanistic authorities that a treated existing building looks pretty much exactly like it used to be before being treated. And so my question is it possible to well, it's possible to scan the facade with 3D scanning. Would it be possible to print the front sheet of the facade with 3D printing in ETFE?
No, it's a really good question. We never tried it up to now. So the big advantage of ETFE is the low thickness. ETFE film you will get up to a thickness of 500 micron meanwhile. Because it's a little bit tricky to develop the extruding machines for bigger thickness. The bigger the thickness, the higher the forces for the extruders are.
Yeah.
And therefore, at the moment, there's a maximum of 500 micron. With a roll width of, let's say, 2 meters. The film is in maximum 2 meters wide. That's one thing. And the other thing is, I wanted to say is, the big advantage is to realize synclastic or anticlastic surfaces with membrane materials and also with ETFE foils. Synclastic means like a ball, like a surface of a ball, with a double curvature like that. And anticlastic surface is like the mechanically pre-stressed surfaces made of textiles, for example. That is a big advantage of films and fabrics. So if you want to get a rigid surface structure like printed with a 3D printer, I would prefer other materials. Maybe, I don't know, materials that are able to be printed. Maybe also thermoplastic materials. I don't know, maybe PMMA or something like that. But up to now it's impossible with ETFE because of the thickness, because of a different field of applications. Maybe in future we can think about it. It's not without any interest.
Okay, thank you. We have another question over here.
Hi, my name is David and I'm a practicing architect and also a tutor at ULB. You mentioned that ETFE had a good fire resistance. How good is it compared to, let's say, glass?
Yeah, I forgot.
Yeah.
Sorry. Good question. Not really fire resistance, because membranes are so thin, they have no resistance if you think about the time of resistance. F60, T60, whatever, 90 minutes resistance, time of resistance. So if you think about the fire behavior of a membrane facade or a membrane roof, you have to think completely different. If you have a fire below an ETFE foil and with air temperatures above, let's say, 300 degrees, the film will disappear. This is like an open building in case of a fire. The critical thing is if the fire is somewhere else and you have air temperatures of, let's say, less than 200 degrees or something like that, then the film won't melt, and then it's closed. It's not an automatical smoke exhaust. But the good properties regarding to the fire behavior of ETFE foils are, it is classified as BS1D0 according to DIN or to EN 13801. That means B means flame retardancy or low flammability. S1 means a quite good smoke index. That means low smoke emission. And D0 means no burning droplets, or the droplets are self-distinguishing. That means the fire goes out after a few seconds. It's quite good. BS1, D0 is quite good. Additionally, you have no flame spread from one bay or one panel to the next one. If the fire disappears, also the burning behavior of the film disappears and stops. That's good.
Thank you.
And last answer, you have a very low mass. If you think about thickness of 0.2 or 0.25 millimeters, the mass for a fire is quite low. And that's also a big advantage. And therefore, finally, ETFE foils are used as overhead roofing material on top of a stadium, over thousands of heads, thousands of people. Otherwise, it would be impossible to use such a material as a roof for a grandstand, for example.
Thank you. Yeah. Hello, it's Mark Bacol from Art and Build Architects. I have a few questions. We'll just do it and then you see who will answer with me. You talked about a sustainable material. I think it's still coming from petrol chemics. So how do you define sustainability then of it? What is the lasting in time about color stability of the material? So you talked about transparency, but is it color stability assured of the material? And then I have in the past seen application where printed surfaces of the cushions, varying the distance between the two layers, could vary the transparency of the light transmission of the cushion. There was an application for, I think it was at the time in Teflon. But did you try or did you have any experience in variable transparency of the cushions through printing or through thermochromic or photochromic polymers added to it?
Yeah, if you like, I can answer it. Photochromic and thermochromic properties are less mixed, but up to now I've seen such properties only in combination with other materials, but never with ETFE up to now. Maybe in a few years. You
never tried, or are you exploring it?
Yeah, we are not a university or a testing laboratory. We are a building company. Yeah. So also at my time at the university, I didn't realize tests or some steps in this direction. But I know it's existing and done also with other plastic materials. The second question was regarding to the printing and the, we call it pneumatic or medical shading systems. That means nothing else than you print a pattern on the outer layer and you print a pattern on the middle layer of a 3-layer cushion, for example. And then you change the inner pressures of the upper chamber and the lower chamber. And by changing these inner pressures, you can adjust the position of the middle layer. Yeah? If you increase the inner pressure in the lower chamber, the middle layer goes up and will finally coming in the position of the outer layer. And if you if you think that the pattern of the printing is alternating, like a chess square pattern, one is black, one is transparent, next one is black, transparent, and so on. And on the middle layer, it's exactly the other way around. Black here, transparent here. And if you put both layers together, you get an opaque roof without any transmission, or let's say just a few percent, which are going through the gaps or whatever. You cannot print it totally opaque. But let's say the transmission is 1 to 3%, and if you reduce or if you move the middle layer to the ground, in case you increase the pressure in the upper chamber, the middle layer goes down, and then the light can go through the chess pattern. And that's, we call it movable middle layer or numerically shading systems. It's possible.
Yeah, it's still the only possibility.
Yes.
Yeah.
I don't know.
So you don't know any other kind of...
Maybe you have an idea?
No, that was the point.
Yeah, it's a moment. But be careful, if the primary structure is too much curved, if the radius is too small, then it is difficult to realize such a numeric shading system because of the different lengths of the middle layer and the outer layer. Then it is getting very tricky. Then if you have such a system, you can work with two printed middle layers with a small distance, with nearly the same curvature. Then it can work also for curved primary structures. And there was another question from your side, the first one.
Stability and sustainability. Color stability and sustainability of the material itself.
Yeah, sustainability and durability of the material. We think the durability is 30 years. It can be recycled completely to 100% if it's not printed. If it's printed, it is more difficult because you have to remove the printing before you recycle the material. Otherwise, if it's printed, you can burn the material. It's not good. We know it. But another option is to downcycle the material, to use it for other things, but not for transparent films anymore. That's regarding to the recycling and the durability. I already told you that the durability is approximately, let's say, 30 years or so, but could be much more, but we don't know at the moment. Could also be 50 years, but nobody knows it exactly. And regarding to the durability of the printing or the color.
No, not really the printing, but the color itself of the film.
Yeah. Which, normally, you can produce so-called master batches. That means transparent film where a colored resin has been mixed to the transparent resin. Let's say red, blue, green, whatever, with different densities and different darkness of the colors. There exists a ISO test procedure, a code, where the colors are, according to which the colors are tested, due to their durability. That means the shifting from red to purple or from red is ISO test procedure, a code, where the colors are, according to which the colors are tested, due to their durability. That means the shifting from red to purple or from red to green, whatever, and it is exactly defined how to test and how to judge about the results. So every color has a different changing behavior and a different durability. And we are not material producers. You can get, for example, ETFE foils from AGC in Japan, from Novofol in Germany, or from Patti in Italy. And all suppliers are using different methods to mix colors into the transparent resin, and they try to find out the best options for their colors to get finally the best durability. I know some colors are not resistant over the time.
But the transparent film itself, if I think about PMMA or polycarbonate, they tend to become yellowish at the time. What about?
It is not significant for ETFE foils. In this issue, ETFE foils are much better than other transparent plastic materials.
Thank you. Okay, thank you. Before we go on to the next question, I just want to check Armando, he has to leave for a flight at some point.
Yes. Thank you very much.
You have,
I must leave to the airport because I'm losing my flight.
Okay, so we'll lose Armando now at this point. But we have another question. Yeah, so please go ahead.
So, Pierre Nicolai, architect, working in Belgium. My question is, can you produce cushions with the lower face completely flat, like this ceiling, and the upper face should be, of course, a volume. So my intention is to produce not facade but roofs, active roofs, giving light when necessary, artificial light, or not when not necessary, or producing energy to lighting direct from under. So if you have energy, you can use light for projecting light under this face, the flat face. You understand?
Mm-hmm.
And so the last part of the question is there? Do you have transparent EFTA film? But if you project light, it is white because it is semi-transparent. It receives natural light during the day, and during the night, the energy produce a white ceiling. You understand? So it's for residential purpose and not for imaging or communication. It's more oriented to the needs of a residential.
Shall I answer?
Yes, please.
The first question was if the inner layer could be flat or planar, and the outer layer is curved.
Well, the other layer is free, but
It's free.
I need a contrast.
Okay, the outer layer is free. So, in the first line, this is a physical question. That means if you pump something up and give space and overpressure, it is automatically curved. Therefore, if it's an inflated cushion, it is both layers, the outer and the inner layer, are curved. But you can imagine there's a cushion on top with curved layers, and below you implement planar, mechanically pre-stressed level or pre-stressed layer. Then you can achieve what you want.
Or thinner membrane.
Or for the mechanical layer, you can take what you want. You can take a mesh, you can take a fabric with a closed structure, or also ETFE foil. And if you want to take it as a screen or like a cinema or whatever, you can use or apply special printings made of silver pigments or white, gray, whatever. And regarding to the energy aspect, we are working on a solution to develop ETFE foil with a metallic surface by using the method of sputtering. A very low thickness of metallic pigments on top of the film or on the surface of the film. But it is still in progress, and it is in progress since more than 10 years. It is very difficult to find the right metal which is compatible with ETFE. The first years the groups of researchers tried to take aluminium. It doesn't work, or it didn't work. Then silver as metal, today gold, very thin. So let's see. I think in a few years we will have such metallic sputtered low E foils made of ETFE. And that is really a break even. That is a good opportunity for our business and for the material to be used also for other things, because exactly what you said, at night or in the night, the energy loss in the direction of the dark and cold space is terrible. Yeah? You will lose a lot of energy. For example, for swimming pools, all the heat goes out through the transparent roof. And if you use such a metallic surface inside, the heat in the infrared spectrum can be reflected or will be reflected. And everybody in this branch or in this field want to get this metallic low E ETFE film. But up to now it is not available. And we are not a producer of materials. We use the material, we apply it as a manufacturer of membranes or membrane constructions, but in the first line the supplier of the material are asked to develop such a material.
In relation to his first question, I'm just thinking that maybe in relation to his first question, Karsten, I'm thinking that if you manage to design a structure who is able to bear, without inflating, two parallel layers, keeping the air, let's say, tight,
That's what
you would get the effect without inflating, and you would avoid the curve. But I don't know if this is what you have in mind.
Yes, the purpose is to receive the light, the natural light when there is light. When there is too much light, to control it. When it's dark, to be a surface, to illuminate the rooms. Because today we have various layers and lights, and it is a mesh of everything, and we need a structure, and it is heavy. And finally, it could be simple.
Should be. You have to think about that. Inflating is going to keep things not parallel, of course. Like, I agree with that.
Just one comment concerning the issue of losing the energy. You can imagine that also if you have PV, PV can also work with the light on the inside, so you could also reuse the energy at a certain extent.
But I thought the problem of insulation could be solved by producing heat.
Yeah. But what I say is that you say I'm losing. Yeah, of course you are losing energy. However, if you have a BIPV with PV technology in that roof, that kind of roof, it will produce electricity out of that radiation that you are losing. The same that can be produced by a wall or something that has PV on it. So it's going further on the use or the reuse of energy that we have around.
Okay, thank you. So we only have 5 minutes left. I'd like to get one more question here, and if there are more questions afterwards, then of course there's a chance to discuss over the cocktail afterwards. So one more question here, and then maybe just to finish off with a couple from the system.
Thank you very much. Good evening. I'm Paul Kartevets from the GUI Group, construction company. One question, I'm not practical of those systems, but in one of the cases you have also pressure that has to be maintained, in the sense that is there energy that has to be spent to maintain certain pressure?
Yeah.
So I mean, because I saw the two cases. Pressure
the
at
example
installation,
in
when you
UH.
install it was temporary installation, permanent installation, so there's an energy expenditure. We have to use energy to maintain the pressure. And my other question is just a comment. We live in a nasty world, so voluntary damage. If anyone comes with the idea of damaging the elements, I mean, you talked about hail, but if people come, I don't know, with arrows or anything, even if you have 4 layers, and or a machine gun, I don't know, blow holes in the whole thing, it's maybe easily repairable, but I mean, we live in a nasty world. How do we do?
Yeah, you are completely correct, and it's right. Normally we avoid to use such thin film structures in the ground level. So we need a height of, let's say, 3 meters. Also at the Allianz Arena in Munich, you have a fence inside, a metallic fence. That's a fence. Cannot touch the films and cannot damage it. The problem of vandalism is known. But if somebody will shoot into such a membrane roof, you get a hole there, and the air can go out through this hole. Normally, if the hole or the damage is small, let's say a few centimeters, you can repair it, you can tape it with ETFE adhesive tape, temporary, or if you have a maintenance concept, you can change the ETFE tape from time to time, let's say every 2, 3, 4 years, whatever. And if the damage is too big, you should replace the layer, or finally, if it doesn't help, you should replace the completed element. But it's not dangerous. Especially the ETFE for cushions are already calculated, or let's say other way around. The structural analysis report always includes the load case breakdown of the air supply. If you think you have 2 cushions, one on the left hand, one on the right hand, and one is completely damaged, you get horizontal forces in the direction of the cushion, which is that's nothing, and you have to consider this case also for the primary structure.
Okay, thank you. So just 1 or 2 questions online. I'll go for a very simple one. Will the presentations be circulated? Yes. Everything will be on the ETFE-MFM.eu website, hopefully next week. Armando said in the video that hopefully in 5 years' time, the module would be, the ETFE-MFM module would be everywhere. We had a question, when would the MFM module realistically be on the market? So to expand on this, perhaps what are the further boundaries to commercialization of the development? And
we are doing the economic analysis. I mean, we are gathering data in relation to the, let's say, I mean, we have the price we have paid for this demo, the research price. We have all the economics, and as let's say construction company, let's say we have the role to develop a report where we will assess the economic of this formula. We have to think of the maturity of the technology. And this is a solution which is not a single technology solution. There are several technologies which are integrating a new system. So each of the components is having a different maturity level. When we apply economies of scale and industrial production of the technologies componing the system, we will have to see the numbers. I mean, we will be assessing that. It will be theoretically let's say justified, because it will be a prediction of what's going to happen in the future. Of course, the best way for the system to be on the market is the public acceptance. Let's say so. If Taiyo starts to receive orders of these systems, they will adapt the factory, and everything will start to be participating in economies of scale. So the cheaper it will become, and the easier it will be for people to install this. We will see the conclusions at the end of November when the document is finished. But according to the first estimations that we have now, this is going to be competitive in the sense that if you want to compare the triple solution with the PV, LED, and plastic,
to what you can do now with the building. So you need to look for a contractor to install the lights on a glass facade. You need to look for another contractor to install the PV. And then the prices of installation of the technologies separately is going to raise traditional prices. So if you have the triple solution at the same time, installation cost is going to make it probably competitive, but it's just preliminary at this moment.
Yeah, and also concerning the product in the market, still left the issue of the testing for certification with a real, let's say, product to be put on that. So there are some, let's say, tweaks and improvements on the technology, on the integration of everything together in order to pass those tests that will allow the product to live for, let's say, many years. This product, I'm speaking of the one that has all the PV and LED integrated onto it. So there will be necessary also to have a certification in the sense of testing for real durability, safety, and also constructive aspects. So maybe this, you say, or Armando said, the 5 years, maybe a little bit less. Let's be optimistic. However, yeah, that could be maybe 3 years or so could be the product in the market.
Thank you. I'd like to just close with one last question from this, and perhaps we can just get a statement from each of our speakers. The question asks, as an architect, why would I want to use this? And I think maybe it means ETFE rather than the MFM. And why would my client want to pay for it?
I can say just one sentence and maybe give the ground to you guys. I saw a video I mean, when we won the contract for this new airport in Mexico, the Norman Foster was, I mean, there's lots of videos in YouTube, and one of the reasons for him to choose this material is because it's really lightweight. So whenever designing a big space indoor in a public building like an airport, they are supposed to be capable of designing big spaces without any bearing support. And this is really nice in visual. If you Google new City of Mexico airport, you will see indoor render 3D modules, images, and the spaces are really wide. So for this architect, which is well known, the main reason was the capability to have huge surfaces without any supporting element, because the material is really lightweight. That's just one reason.
Well, I'm a PV specialist, so for me the interesting thing of the ETFE is that it's a very good product to be part of building something using PV on it. Maybe printing the PV on it, maybe there are many things that can be done through ETFE. And concerning the architects, of course, is the versatility of this material and the possibilities that can be done through this material for roof, for facade, or for many other applications, as you have been seen on the pictures presented already. And your imagination probably will go farther away.
No, I think the architects are using this material because it seems so innovative on the one hand, on the other hand it allows a lot of different applications. That's ago, and he saw the model of the Allianz Arena from the architects Herzog de Meuron, the preliminary or initial design, and he said, that's it, nothing else, I want that. Yeah, it's really a completely different architecture and kind of shapes. Anticlastic surfaces or synclastic surfaces you cannot achieve with other materials, and that is maybe also one reason.
Okay, thank you. So if there are any more questions here, then you have a chance to attack our speakers over a glass of wine. Thank you to those who joined online, and thank you also to everyone who has been here today. Again, all of the materials will be available on the project website, hopefully next week or the week after. So please feel free to follow up. Thank you.